Phase diagrams. In this chapter, we will identify what phase diagrams are. For a given phase diagram, you'll need to identify the state or states of matter that are present and find the triple point. Given enough information, you should also be able to sketch one of these yourselves. A phase diagram, much as you would expect, is a diagram which shows all of the phases of a substance. The ones that we are going to be dealing with are simple 2D graphs with temperature on the x-axis and pressure on the y-axis. Though they can definitely get far more complex than this, and if you just do a quick Google image search, you can find some of these. Wherever there is a line, that's where two different states are stable. So for an example of this, think about ice water. If we kept ice water at exactly 0 degrees Celsius, then there would stay some water and some ice. That's a liquid to solid transition line. There is this equilibrium for other phases as well. So you could also have a place where a gas and a liquid exist together, or a gas and a solid exist together. Another point, called the triple point, occurs when all three phases are in equilibrium. So for example, if we had water, this would mean that you would have boiling ice water. There is also a point called the critical point that we don't use too much in this class, but it's good to identify. Past this critical point is a supercritical fluid. Now let's answer some sample questions using a phase diagram. I have here the phase diagram of carbon dioxide. If a sample is at negative 78.5 degrees Celsius in 5.5 atmospheres and is then heated, what transition will occur? Take a moment and answer this before moving on. Let's draw an arrow showing what's happening. Since it crosses from a solid into a liquid, the sample will melt. But then, if it keeps being heated, it will eventually cross the liquid-gas line as well. And therefore, it will boil. So first it will melt, and then it will boil. Now let's look at another example. A sample at negative 78.5 degrees and 4.5 atmospheres is heated. Take a moment and answer this before moving on. In this case, it's going to be crossing over the solid-gas transition line. And so we call this sublimating. Let's do one last problem with the carbon dioxide example. Now a sample, still originally at negative 78.5 degrees Celsius, but this time at 0.9 atmospheres, is placed under a greater pressure. So this time, instead of changing temperature, we're changing pressure. What transition is going to occur? Take a moment and solve this before moving on. Let's draw our line again and see what line it crosses. Since it's going to cross from a gas into a solid, this means that the sample is undergoing deposition. Now let's look at something that is unique to water. Here I have our carbon dioxide example and a diagram of water. Take a minute and look at the differences between the two. I know there's a lot, and I'll focus your attention when we come back on them in a minute. Now, of course, they all have different points and different temperatures and different pressures because these are different species. But also notice the slope of the liquid-solid transition line. So focus on the slope of the liquid-solid transition line for a minute. In carbon dioxide, as you increase the pressure, you go from a liquid to a solid. This is very normal. Most substances are more dense as a solid, and so whenever you increase the pressure, it's going to switch it from a liquid to a solid to more densely pack it. But look at water a minute. What happens in water around that transition line as you increase the pressure? In water, you actually do the opposite. You go from a solid to a liquid. And this is because ice is actually less dense than liquid water. And so by increasing the pressure, you need to increase the density, and it switches it to a liquid. And this is a really important difference because it means that ice floats. Most other species, the solid would not float. Without that, life in cold climates would be far, far more difficult because lakes, for instance, would freeze and then the ice would drop, and then the top would freeze and the ice would drop, and the entire lake would freeze solid. In review, a phase diagram tells us about the phases at a variety of temperatures and pressures. On a line, 2 phases exist in equilibrium. At the triple point, all 3 of these exist.